Hello everyone, welcome back. I hope you had a great lunch, and now that we are post the very fiery lightning talks, we'll start with this track's first talk for the second session. We have Shaleen Jain here, who's going to give a talk on scaling Python for performance. So can we have a quick round of applause for Shaleen?
I know this is a post-lunch session, but I'll try to be as interactive, as fiery as I can. What does this slide represent? This hourglass is what we do. The flash is what production wants. Okay. Now, my topic for today is scaling Python for performance, a 40x faster image processing with smarter design. I'll go in detail with every term of it. Basically, first I'll tell who am I. I'm Shaleen Jain. I did my master's in 2016 from HBNI Mumbai, then worked for 8 years at Bhabha Atomic Research Center in X-ray imaging and neutron imaging. And also, not just that, I started my image processing journey a little early in my grad days using some amateur image processing robots, color tracing robots, object capturing robots, all those kind of things. And then this image processing didn't stop me finding a new job. So here in Applied, I'm with Applied Materials for 3 years now. And there we do optical wafer inspection. And I work there as an algorithm developer. As an algorithm developer in optical wafer inspection, our job is to find defects on wafer in semiconductor manufacturing processes. After every process, there can be many defects induced due to process, due to tool, due to many kind of things. And our job, and generally the analogy which is given is like to find a defect on a wafer is like finding an ant in the Manhattan, or in Bangalore context, maybe to find an ant in maybe the Whitefield area. So that's how rare event, that's how small thing that is. So it requires a lot of image processing. Apart from this image processing world, I'm married, have a beautiful kid, and I love hiking, some Himalayas, some Siadri treks. I read a lot of Hindi books and cook, so that's me. Now coming to the topic, have you ever felt stuck? I'm not talking about the Marathali bridge or silk board. I'm just talking about, have you ever felt stuck during programming? We all have been. One of the case I'll be discussing here, I went to my close friend nowadays, Copilot, that what's the language share in computation heavy development today? What is the percentage share of different languages? And I think there's no-brainer, but the number I can show you, it says 30% of the new code which is being developed, it is being developed in Python. But the next question I asked him, is Python scalable easily for CPU-bound tasks? Okay, it can be scaled for IO-bound tasks, but when I have a CPU-bound task like image processing, can it be scaled easily? So the answer it gave me, for CPU-bound tasks, Python is not easily scalable out of the box. So this is why I am saying we are stuck in a kind of loop. But there is a but here in the answer itself. It can be scaled with right tools and strategies. This talk is we will be talking about those tools and strategies. How can we do that? To talk about it, I am taking an example, a case study of image segmentation. What is an image segmentation? Given an input image, we want to pixel by pixel classify out that this pixel belongs to which class of the object. We are familiar with segmentation, maybe not with the term, but we see it every day by day activities. Maybe we see in some self-driving car where the driving car automatically pixels out the road and the cars. Sometimes some defects are there in our scenario. Sometimes in some industrial domain, there are some defects are there. Or in brain tumor segmentation, I want to segment out the tumorous segment outside. Or maybe in some satellite image, I want to segment out different areas as, let's say, road, gardens, fields, and rivers, and whatnot. This is the process of image segmentation. I just talked about it, so that we can all come to a single page. Now, when this image segmentation happens, sometimes To process these these segmentation map, these are called segmentation map, the ones you are seeing on the screen right now, the output is a segmentation map, but it is as big as the input image. And when I'm talking about handling gigapixels of data, it is impossible to save the segmentation map. So the next problem comes out that I want to convert the segmentation map into a list of rectangle. Okay, this seems easy. I can just draw a bigger rectangle out of all my segmentation map and call it, okay, this is a rectangle. No, I don't want those kind of rectangle. I want a rectangle which is exactly having only the pixels which are just segmented, or which just have the area of my interest and does not cover even a single pixel which is not of my interest. You might have seen some application of bounding boxes, if you might be familiar with YOLO a little, that it gives us a bounding box, but that bounding box also contains some pixels which are not of my interest. I want to convert each pixel of mine, which I just segmented out, as a list of rectangles. It has many applications for gigapixel satellite imagery. I want to exactly mark every pixel of mine in my satellite images, but satellite images are huge. I cannot store always the satellite image. I want to compress my data and make my job easy. Also, in pathological image processing, suppose you are doing a brain tumor segmentation, and you segmented it very nicely. But after that, what did you do to store it as a rectangle? You made a bounding box. You just killed the whole purpose of segmentation. So we want something which can give me exact those pixels only in my rectangle. So first I went to the internet. Let's see what are the solution available. I found, okay, there is a minimum bounding rectangle, MBR, which we all are familiar with, but that is not my use case. Or some very mathematical graph-based method exists which can only divide the rectilinear polygons and cannot convert the irregular shapes. So these were the problems. So as a solution, what did we do? We wrote from scratch a greedy program algorithm which efficiently computes this maximum coverage of the rectangles, coverage of the island into rectangle. Then what does this algorithm do? That is my second point that I'll tell you in detail as I go in the flow charts from the next slide onward. The third part is actually where we want to focus in this talk. Implementation is designed to be adaptable to various problems. The final implementation which I want to share with you guys, which we did, is adaptable not only to image processing domain. If you have any CPU-bound task, you can replace my task with your task, and that will be a very efficient way to optimize your throughput. And that utilizes the multiprocessing in a better way so that we can improve the throughput. Okay, now coming to the second part. So this is actually the third point is my main focus of the topic. Coming to the second part again, the algorithm first find the connected component. I am not able to understand through this text. Let's see a flowchart about it. What can be a simple procedure to convert a complete segmentation map to a list of rectangle? The first, we get an input map of segmentation map. We find all connected components from it. What is a connected component? So in a binary image, all those pixels which are, let's say, true and are next to each other with some neighborhood logic, or either 8 or more than that. So either whatever the nearby pixels are there, they'll be called as one connected component. As you can see in this picture, that this black man is one connected component, this pole is one connected component. So my first step is to find all the connected components. How can I do it? There's a great library called OpenCV, which is developed initially by Intel, and then from open source community, it grown up a lot. I can easily use a cv2.connected component. It has a good Python wrapper, which is also very good scalable kind of thing. So I can get all the connected components, and not just the number of connected components, I can get all the kind of properties, what is the bounding box, what is the area, from where it starts, everything I can get from there. Okay, so my first step is to find connected component. Find connected component, and then for each connected component, I proceed with my algorithm. Let's say this is my one connected component which I got after processing my image at the first step. For this connected component, I find the maximum rectangle. So this find maximum rectangle is the actual algorithm, which is very computational heavy algorithm, which take care of a lot of image processing, a lot of array manipulation, NumPy array manipulation it does. So find the maximum rectangle out of this connected component. Okay, that has been written from the scratch in this given example. Okay, this is my maximum rectangle. I obtain the mask rectangle. Here, I get this. I mask the obtained rectangle. And now my definition becomes recursive in nature, as now again I'm left with few more connected components. For each connected component, I'll find the maximum rectangle, mask the rectangle, and this will go on and on and on, and this will solve my problem. Seems very easy. This is my basic solution approach. I can call it sequential approach. Can I deploy it? Did I try to deploy it? Okay, I tried to deploy it. What happened? We are working with gigapixel images. The almost size is 8,000 cross 300K pixel images, which are huge in size. Huge. And the issue is, if I do it sequentially, it is nearly an impossible task. And we know the GIL, the glorious GIL we talk about again and again in Python, that can't let me use the multi-threading. So what is a GIL? It is a global interpreter lock. So it let you create the threads, but two threads of the same process cannot acquire or cannot run in two different CPUs. So even if I have multi-core, which we all do and our servers do, but we still cannot utilize those multi-cores of our CPU. So GIL cannot do it. So okay, no problem. We also have multiprocessing libraries in my Python stack. I will use those. So if I ask you, in this basic solution approach, in this sequential approach, what is the place first you will want to tackle and want to apply this multiprocessing? The answer is quite simple: for each. Wherever we see for each, I can parallelize it. Okay, so that's the first approach we did. I converted this for each component. That's why at first I just described the complete algorithm to all of us, so that we can understand and follow the slides. Okay, for each connected component, we make a process, and inside that process, I again follow the same steps. For one connected component, find the maximum rectangle, mask the obtained rectangle, and then find the connected component. Now here I'm stuck. Should I fork new processes from here? Should I fork new processes from here? So to fork a process from a child process, it's very big no-no. We all know this. Why it's a big no-no? Because the grandparent process, if somehow, if I did, the grandparent process will not have any record of the grandchild process, and the whole memory, the whole throughput, it will become a mess. So now I do not have an option. What I did in this Naïve multiprocessing approach, again, after one step of utilizing the multiprocessing, I just have to rewrite a recursion there, because my problem definition is recursive, because I can only work whatever is left by the previous step. So then recursively, I take one connected component, find the maximum rectangle, mask the obtained rectangle, and again and again and again. How can we do this in Python? We have a good multiprocessing library. We can import it, and then we can have some process pool, and then process pool.starMap. I can do, okay, find my maximum rectangles, give it the arguments. It will work. It will work. Did it work in our case? Did it induce any problem? Let's move to the next slide. So in Python, the depth of recursion is limited to 1,000. It may be increased a little, but still there is a limit. And because I show we are working in a gigapixel image-based situation, I exhausted the depth of recursion of 1,000. The size of stack kept growing because I am going down the depth of recursion. My stack size kept growing. I am not even deleting the variables. I had a severe throughput hit. This severe throughput hit is just not because I am just underutilizing the multiprocessing, but also because in every recursion step, I assign new image, that image size again and again, and to allocate a memory itself is a big throughput hit. And also, a very specific pattern started creating a problem. What is that? What is that problematic structure? It is a waffle-like structure. Why I'm calling it a waffle? Let's see the structure. This whole purple area is my area of interest. And all the yellow area is not area of my interest. And I want to get out the rectangles. As many times I kept taking out one rectangle, masking, and find the next connected component, I am still left with the same connected component I started working with. So that kind of problem we faced, and that created a problem. So this waffle-like structure started creating a problem. Okay, when there's a problem, there's a solution. We opted out for some solutions. First four are some few general ones. The last one I'll talk in detail. Okay, deciding data type in runtime, we often misvalue it, or we very much do not value it much. That it is, because I'm working with gigapixel images, better to, because OpenCV as an output give me a float 32-bit images, which I might not be using. Sometimes it's okay to use in 16 images only. That also saves a lot of cost. Sharing big variables across processes through manager. Here comes the picture. When we share, when we fork some threads, when we initiate some threads, all the variables which are to be shared, because they are of the same process, are shared across the threads. But when we do it in a multiprocessing way, each process is a separate entity. And if we want to explicitly share, like in my image, I want to share my one big image because each of my process will be working on the same image, at least reading the data from the same image. I want to share that. So I can do it by a Python module called manager. It's not your manager, it's the Python manager. Manager is the name. And then deleting unused variable and invoking garbage collector. I think there was a very good talk today only by Puneet and Jitu in track 2 and track 3 about this. I won't go in detail. It can be a talk in itself that I can explicitly call the garbage collector if required, if my process is something like that. Another is using Numba. What is a Numba? Numba is an accelerator-friendly library, which is a just-in-time type of compiler, which pre-compiles your some computational heavy code. For my case, that finding the maximal rectangle. If I can convert and use that in my Numba, okay, that helped. These are few small steps, but here the main culprit was recursion. Still, even if I use all this and do not prune the recursion, my memory will keep increasing. I will have a severe throughput. So the next step is pruning recursion. How can I do that, pruning recursion? Like stopping the recursion or removing the recursion altogether itself from the program. How can I do it? Okay, this was my previous approach, Naïve multiprocessing approach. For each connected component, I was making a process. I wanted at this step, when I am finding a new connected component, I want to send it to the parent process again. And somehow, let the parent process take care of it. So what can I do? What can I do? I change the architecture. From Naïve multiprocessing approach, I've gone to queue-based multiprocessing approach. This is the final one which we used. What did we do here? We have an input segmentation map as earlier, find connected components, okay? For each connected component, now I want to make for each connected component as a task. Because from each connected component, I want to get out the rectangles. For each connected component, I make it as a task. and append it to a task queue, which I'll be processing later. And then I process this queue asynchronously. What do you mean by asynchronously? That I process this and do not wait for results to come. I attach a callback there and let the callback handle that whole process altogether. So in this manner, it happens. Now let's see what is the process of a task, what happens inside a task. Also, for each connected components, I share the variables across the processes. My big image, my list of rectangle, my task queues, because all of these processes need to be accessed by all of my processes. And when we do it through manager, through Python manager, and not using pipes or some loose IPC communication based, when we do it through manager, the locking mechanism, the synchronization, the Python takes care for it. What do I do inside a task? The process gets starts, find the maximum rectangle, asynchronous dispatch of the results. We dispatch the results and rely the callback to catch it. Then mask the obtained rectangle. For rest of the image, find the connected components. Now, instead of going recursively, for each connected component, I make it as a task. And now, append this task to the same task queue on which my parent process is working on. So in this manner, I change my recursive implementation to a task queue-based iterative implementation. And now my individual process is a very small process. It has one job. It just needs to find one maximal rectangle out of it, and then send the rest of the task to the parent process and take care out of it. So instead, going deep down inside one process to find all the rectangles, I kind of change it to a BFS kind of method where I'm going in the breadth first. So this is how we changed. Okay, if flowchart was not enough, I just took the snapshot of the code. That, okay, I have a manager. With that manager, I share the queue across all the processes, the rectangle list across all the processes, and then the max label. This is what something my algorithm use internally. And while up till not the task queue is empty, I keep taking out the processes, keep computing, and then at the end, pool.map async. This is a asynchronous call where I give this my compute function, which is my kind of partial function. I give this a compute function, and the tasks, what are the tasks individually defined, and attach a result callback. This implementation can be used in any CPU-bound based approach. This need not to be an image processing problem. It can be whatever your compute task is. If it is a CPU-bound, this is a solution which you can implement. Also, a similar implementation also can be, we can also get through ProcessPoolExecutor, which is a Python module, which it also have a similar functionality, but this one gives me a little more control. How do I want to control it? So that's the way. Okay, let's summarize. What are the speedway employed accelerator-friendly libraries like Numba, data type at runtime, recursion into iteration, very basic engineering, all these things we have maybe learned. And then maintaining a process pool and reuse a single copy instead of spawning recursive processes, because if we do not maintain this thing, like sharing variables across the processes, again the memory allocation will take a lot of time. One also takeaway, we need to profile our memory and throughput, because what we do not measure, we do not optimize. This is not my saying. Puneet said that this in the previous talk in track 2. It was a great talk. But yes, so here coming back, maintain a process pool and reuse a single copy instead of instantiating every time, in new process. Let's use a single copy. Do I get a good result? Yes, I did. I did the experiment in various data sets. Here I'm showing you 4. These are 4 first two are my in-house scan data set, like which are actual wafer scans. The resolutions are 8,000 cross 200K. And initially, my sequential approach, the first approach was taking 1100 seconds, which was from product side, it said, okay, we cannot release it. Okay, 1100 seconds. My Naïve multiprocessing approach, okay, decreased to 25 seconds. And then my queue-based approach, reduce it to 18 seconds. I just make the problem double, just did some manipulation with this in-house scan data set, and initially 3,500 seconds, that reduced to 28 seconds. To test more for rigorous testing, I made some synthetic data sets, the synthetic waffle-like data set which I showed you earlier. Sequential approach was taking 200 seconds. The queue-based could do in 4 seconds. Then I made the algorithm job a hell. I made a very, very problematic data set where I gave a very fine, minute waffle-like structure with sequential and Naïve multiprocessing approach could not even complete in weeks. At least queue-based could have did it in 400 seconds. So here, okay, I get an impressive 40-fold improvement. What is my summary of this talk? That, okay, the algorithm was written, it's good. The implementation of the algorithm utilizes multiprocessing, which is also good, but the actual key lies that instead of directly relying on the high-level abstractions, we can smartly design the solution approach. Python is powerful, but your designing matters a lot. So sometimes, instead of relying directly on, if I have an optimization problem, I search for a library. Instead of searching for a library, let's try to redefine our problem in such a way so that I can better utilize the underlying libraries, underlying hardware. This is my key takeaway from this whole slide. Thank you so much. Do you have any questions? If I have time, I can take those. Can you take a question? Okay. No questions? Okay, thank you so much. Thank you so much.
Excuse me? Am I audible?
Yes, yes.
Yeah, I actually had one question. So, firstly, lovely presentation. Thank you. We basically ran into the very similar problem previously, and the CPU-bound problem that we have in Python, and we just use FFI, foreign function interface, and use PyOxide so that you can transfer your CPU-bound tasks to, let's say, Rust, right? And let the abstraction be used directly in Python. So I'm just trying to wonder, why didn't you just...
Actually, this is a very production-based environment, which I do not have like such facilities. Okay. It is we have tools which are in themselves, they are not cloud. We have something like a complete fixed hardware structure. And I wanted to tackle this problem from whatever I have, like what everyone can have. So everyone might not have that Rust kind of infrastructure.
But foreign function interface can be used in C++ or literally any language, right? So
yes.
You could just transfer that CPU-bound task to C++ and
yes.
Let the abstraction be used directly in Python.
Sorry, I understand your problem. Okay, that also is there. I use Numba for that, for accelerating just that CPU-bound task. But I was explaining the paraphernalia around that. Sometimes that also need to be optimized, just not the main core functionality.
All right. Thank you so much.
Thank you so much. Thank you so much. Okay. Thank you so much.
Excuse me, sorry. I have a question.
Okay. Sure. Where? Sorry.
So in the queue-based approach, you said you used an asynchronous queue. I'm just trying to understand what the thought process behind that was. Why asynchronous?
Asynchronous so that I do not need to wait for the results to come. I just attach a callback there. So just when I also kept seeing the edge top while using this, so I was seeing what I was seeing across I had some 48 cores or something like that. What did I see? As soon as one process gets end, it does not wait the whole one loop of the process to end. Simultaneously, a new process is taken from the task queue and assigned. So I'm saving that time. Because if it can happen, my one connected component is very big, another one is very small. Small one will finish, and that CPU will be idle for the longer time. So better, okay, let it be async, and the next connected component can be processed. Okay, thank you so much. Okay, thank you.